So without further ado, we'll hand over to Pat. Pat, old friend of mine, more than 40 years experience in the motorsport industry, which has seen him achieve huge amounts of success. He started his career designing championship-winning cars for the lower formulae. When he joined the fledgling Tolman F1 team, working with Ayrton Senna, and then with Benetton and Renault. That's where he achieved most of his extraordinary success. So his partnerships with Michael Schumacher and Fernando Alonso produced 32 race wins, 4 drivers' world championships, 3 constructors' world championships. And during this time, he became technical director of the Benetton Formula One team and then the Renault Formula One team. More recently, Pat was the CTO at Williams F1, a position he held until the end of the 2016 season, during which the team achieved many notable successes. Pat's now CTO at Formula One, and that's Formula One management, tasked with setting up a steering group to look at, and the assistance of the FIA, the future F1 regulations, most of which, or the culmination of which, are going to be seen in the 2022 regulations, and Pat's now turning his attention to the role of F1 and the transition of F1 to the low carbon economy. So Pat, without further ado, we'll hand over to you.
Thank you. Well, thank you, Steve. It's a great honour to be speaking to you all here. But I think those of you who might know me might be wondering why, as a competitor for 40 years on the chassis side, am now working for the commercial rights holder, Formula One Management, again, much more on the chassis side. Why am I here tonight talking to you about engines? Well, the simple answer is because the engine guys never talk to anyone. And we thought in Formula One that if we wanted to really contribute to the discussions with the FIA on future regulations, we really needed to understand the engines a little bit better. So we undertook, with Cranfield University, to do some modelling of the current engines and understand the principles that have led to over 50% thermal efficiency. In fact, the engines are now running around 52%. So although this lecture is called The Road to 50, we've actually gone through that. But anyway, as a chassis guy, please forgive me if a little bit of the detail is sparse, but I'll try and fill in the bits that I do know. So before we discuss the current power unit, let's have a little look back at the last couple of normally aspirated power units that we've had in Formula One. Between 1995 and 2005, we had the 3-litre V10, great engine. We moved on to the V8 after that, and finally in 2014 we went to the engine that people are familiar with now, the 1.6-litre V6 turbo hybrid. And if we examine each one of these just briefly before we move on, the 3-litre, the V10, great engine, as I say. I think the main features of this era were the race really to get the weight down, because the early V10s weighed around 120, 130 kilograms. And Cosworth and Ilmore were the first people to produce really lightweight engines. Cosworth, in fact, dropped 36 kilograms off their engine, which is about 30% of the weight, and it really was quite astonishing. At the same time, there was a big push to get engine speeds up, and by the end of this era, the V10s were running at around 18,500 RPM and producing, as you can see, around 930 horsepower, brake-specific fuel consumption at maximum power, because that's where we're interested, just under 280 grams kilowatt hour. We then went on in 2006 to introduce the V8. And this was effectively 8/10 of the V10, but a lot more prescriptions were introduced. For example, the bore was set to 98 millimetres, and the weight, even though the engine was slightly smaller, was actually increased to 95 kilograms. And the reason for this was really to limit the runaway budgets that were being spent on engine development at the time, both in exploring all aspects of the design space and also the huge cost of some of the ultra-lightweight components that were going on these engines. Now, discussing the efficiency of this engine is a little bit difficult. I've put the thermal efficiency down as 30%, and I think that's probably what it could be measured as on the dyno. But this was an era when the aerodynamicists were really using the engine to augment the aerodynamics, augment the downforce. And the real trick there, apart from a bit of judicious placement of the exhaust, was to really increase the momentum ratio of the exhaust gases. And this definitely led to some suboptimal engine efficiency in some of the operating areas. But the race was still on for engine speed, and once again it was Cosworth who led the field, and they were the first to reach 20,000 RPM with one of these engines. But it really was a bit of a case of diminishing returns, as the high engine speed, even though we had volumetric efficiencies of around 120%, they may have introduced more air, but really that power was sapped by the increased friction. And it was also rather difficult to maintain that sort of volumetric efficiency. In fact, it was impossible to maintain that volumetric efficiency right through the rev range. So these engines tended to have rather lumpy sort of power curves, and they were actually quite difficult engines to drive. Over the course of the life of this engine, the regulators brought the engine speeds down, and they attempted to eliminate exhaust blowing, I have to say with pretty limited success. But something I'm quite proud of is that my team at that time, which was Renault, we won the last race of the 3-litre V10 era and the first of the 2.4-litre V8 era, so I have some quite fond memories of those engines. But in 2014, a totally new approach was taken. The V8s had adopted some mild hybridisation in 2009, and a 60 kilowatt electric motor and a relatively small battery was fitted to those cars, just really only for kinetic energy recovery, nothing else. But in 2014, we decided to reduce the engine size again, went to 6 cylinders, 1600 cc, but now a turbocharged engine. For the first time for many years, turbochargers had been popular in the 80s. And we added a 120 kilowatt kinetic energy recovery system. But these changes alone, though, were not the most significant. To drive towards higher efficiency, two limitations were put on the fuel. The first was that a maximum fuel flow rate was introduced of 100 kilograms an hour, and the second was that the maximum fuel usage for the 300 kilometre races was 100 kilograms, which was around 2/3 of the fuel used by the V8s in a race. So suddenly, after years of developing engines to ingest as much air as possible and then simply adding the right amount of fuel, the target was reversed. And this led to a fundamental change in thinking and drove developers to much leaner burn engines. Also introduced in 2014 was a second electrical machine, which we called the MGUH, the motor generator unit from the heat side. This focused on additional energy recovery from the exhaust heat beyond that achieved by the turbocharger itself, and it consisted of a high-speed MGU attached to the turbo, which both recovered energy and acted as a motor to eliminate turbo lag. And it's this engine that we'll focus on a little bit more tonight. So let's look at some of the fundamentals of the current engine, and in so doing, look at the road to 50% efficiency. Firstly, the fuel limitation was an absolutely unprecedented change, as I said before. It really had changed the whole philosophy of power production, and fuel flow was limited to 100 kilograms an hour at 10,500 RPM. And up to this speed, it had to follow the law which is illustrated here. Now, this had several consequences, but the most significant of which was the search to run the engines very lean, which in turn led to the development of several new technologies. And as you can imagine, it also meant that the rev limitation was really irrelevant now. There was not much point in going much above 10,500 RPM because you were now limited on fuel. So by simulation, you could see that shifting gears a little bit above that was worthwhile, but not a lot more. So let's talk about some of these things we've done on the road to 50% efficiency. Firstly, the Formula One engines run highly diluted, so lambda is around 1.3 to 1.4. And the objective of this is to achieve full combustion limit the heat transfer to the coolant, and increase the cylinder pressures and temperatures. But a high lambda also means a high mass flow and thus a high enthalpy flow to the exhaust. So if we're recovering from the exhaust, we want that high enthalpy. And this leads to a larger proportion of the fuel energy that can be recovered by the turbine. And when we're achieving around 50% efficiency, we've got about 4/5 of that coming from the engine and about 1/5 from the turbine. And the current engines employ numerous different control strategies to maximise the performance in all modes. And by modes, I mean modes like those where we're using electrical recovery, electrical deployment, or what we call race neutral, where the objective is to maintain a constant state of charge in the battery. The strategies are pretty complex, making use of wastegate control and harvesting of energy from the electrical machine attached to the turbine, which can then deliver that energy directly to the machine that's connected to the crankshaft, thereby bypassing the battery and delivering power irrespective of the state of charge of the battery. For maximum performance on the qualifying lap, the wastegate is used to control boost pressure, so we minimise the exhaust back pressure and we get maximum ICE power. We add then the electrical energy. We're limited to 4 megajoules a lap of deployment from the battery, but obviously we deploy that fully on a lap, on a qualifying lap, to get maximum performance. But when, as a chassis guy, I first came to manage a design team for one of these cars, one of my real concerns was cooling. The cooling requirements for water were slightly reduced from the V8 engine, but even with the lower engine speeds of the V6, the oil cooling was similar. And I think it's probably due to the high cooling requirements of the pistons, which are cooled by squirt jets. On some engines, this is a separate circuit, so they can run this oil cooler than the oil in the main galleries and allow, through using a dedicated pump, the oil flow to be proportional to engine speed, thus having a cooling flow which is approximately proportional to the heat input, while minimising the oil in the crankcase to reduce heat build-up and churning losses. In addition, the intercooler requirements are quite demanding. Some engines are able to run with remarkably high inlet temperatures, while others are more limited. But the intercooler total load, whether it be an air-air intercooler or an air-water intercooler, and both designs are used on current cars, is around 90 kilowatts, so quite a large device to put in the car. The lower charge temperature is conducive not just to increase power, but to reduce propensity to knock. But low temperatures leave the cooler designers having to really cope with a very low delta T between the ambient air, because we often race in areas where we have quite high ambient temperatures. But we have some limitations. The limitations are misfire and of course the mechanical limits, because the peak cylinder pressures are now getting to be pretty high. We also exploit our high dilution with a high compression ratio. And I think everyone knows that the higher the compression ratio, the higher the potential thermal efficiency. And F1 engines are designed right up to the limit of 18:1, which is a regulatory limit of compression ratio. Now, of course, that can give high thermal efficiencies, but simple maths shows that with a compression ratio of 18 and a charge temperature of 50 degrees centigrade, the temperature at the end of an adiabatic compression process is around 750 degrees. Now, of course, that's an idealised number, and the reality is a little bit different with heat losses, but it does illustrate that the temperature at the end of compression can easily exceed the spontaneous combustion temperature of a lot of hydrocarbon fuels. And this leads to a combustion system that's a little bit difficult to classify. Running with a high compression ratio allows us to do certain things. We can increase the cylinder pressures, which is, of course, where we're getting our power from. We can improve the fuel conversion efficiency, and when we're limited on fuel, that becomes important. And we can explore all these new types of combustion. And it's really different from a conventional pre-mixed one. It's a mix of a homogeneous, a stratified, a diffusion flame, an HCCI and a spark-assisted HCCI. So quite difficult to classify exactly what type of engine a Formula One engine is. However, very advanced control systems are required as temperatures are raised, which increases the risk of abnormal combustion. And the increase in compression ratio is also limited by mechanical issues, as raising the compression ratio increases the peak in cylinder pressures. But the mechanical engineering is realisable. Maintaining lightweight and low inertia is doable, even if difficult. But the need to control the combustion process that's basically operating in an unstable region is where the breakthroughs that have led us to 50% thermal efficiency and beyond lie. So what are these enabling technologies? The combustion process is, to say the least, unusual, and this leads us to think about how we prepare the charge and how we ignite it. One of the secrets of high-performance engine design has always been to get the charge prepared, and this chart shows roughly how we need to alter the charge preparation as we alter designs to increase efficiency. So down at the bottom left, if we compare to a normally aspirated port-injected spark ignition engine, our first gains come from adding turbocharging. With this, we're using exhaust enthalpy for pre-compression of the charge air and thereby increasing the charge density. As we move to direct injection, we get a gain of efficiency because we're increasing the charge density further. We're also increasing the compression ratio by evaporation of the fuel. If we then look at a Miller cycle, we can further increase the apparent compression ratio while lowering the charge temperature and compensating with a larger compressor and a higher boost pressure. But as we're running lean, we now have a mixture that's very difficult to ignite with conventional methods. So perhaps the biggest enabler of increasing thermal efficiency in our engines has been the passive pre-chamber. When the regulations were written for the 2014 engine, it was decreed that only one fuel injector could be used per cylinder, and this led to the development of the passive pre-chamber. So let's look at that in a bit more detail. We need a very advanced ignition system to control this combustion. We have a high risk of misfire when trying to ignite a mixture at lambda 1.4 with a conventional spark plug ignition system. So this led to the introduction of a passive pre-chamber, effectively a spark plug surrounded by a perforated cap. And as only one injector is allowed, this must be directed towards the pre-chamber to create a zone of high fuel density around it and to ensure enough fuel is forced inside during the compression stroke to create a rich mixture in the pre-chamber. And this is necessary because we've got a highly diluted charge for the engine. But perhaps at this point I really should point out the difference between a passive and active pre-chamber. An active pre-chamber has an additional injector delivering fuel straight into the pre-chamber and a further injector which delivers the majority of the fuel into the combustion chamber. A passive pre-chamber, as we use in Formula One, relies on the single injector to deliver the bulk of the fuel into the combustion chamber while ensuring that an amount will find its way into the pre-chamber via the holes through which the ignited fuel will later jet out. Now we claim it's very new, but there's nothing new under the sun, and the pre-chamber has been in common use on gas engines for a number of years, and was even used in the Ricardo Dolphin engine of 1909, which was actually a two-stroke engine. Through the years, various forms have been developed, including these listed here. But today it looks a little bit different to that Dolphin engine, and this is what a current pre-chamber looks like. Bit of an artistic impression, so please don't try and build an engine using this. But in the F1 engine, the pre-chamber is effectively a shroud over the electrodes of the spark plug. The holes are very small as the ignited mixture has to be broken up to a plasma jet as it enters the main cylinder, and yet the holes need to be large enough to capture the fuel at the start of injection. Equally, the position of the holes is critical as they must allow fuel to enter and the plasma jets to reach all parts of the combustion chamber. A couple of weeks ago, I was at the American Grand Prix and I was watching some technicians fitting new plugs to an engine. And believe me, it's an incredibly exacting job to do. So they have to fit the plugs, they have to check the timing against a jig, they then have to take them out, fit spacer washers, try them again. And it reminded me of my days of building engines with shims to get tappet clearance, where you just do it over and over again. And it seems to defy all the maths that you've put into it. But the passive pre-chamber, when the mixture is ignited, it creates turbulent jets of hot gases with free radicals. So effectively it's a plasma. and this improves the combustion of the lean mixture in the main chamber as it creates multiple ignition sites. You can imagine plasma coming out of each one of those holes is really reaching across the combustion chamber. We do need to have efficient residual gas scavenging so that we can ensure that the ignition of the pre-chamber mixture when it comes around for the next cycle. So we saw earlier how we need to prepare the mixture for various types of engine, plasma jets being extremely turbulent part of that process. We also mentioned the problem of scavenging, of charging the pre-chamber, but we mustn't forget we also need to scavenge it very effectively as well. A further technology that enables this type of engine to be so efficient is the Miller cycle. The pre-chamber was a relatively new embodiment of a very old technology. The Miller cycle is only slightly newer, having been patented by Ralph Miller in late 1957. So what's the Miller cycle and how does it help us? Well, with the Miller cycle, the effective compression ratio is reduced relative to the geometric compression ratio, while the effective expansion ratio remains at the geometric ratio. So really quite different to a conventional engine. And this is achieved by an inlet valve that closes before bottom dead centre. So the additional expansion after the inlet valve is closed reduces the temperature in the combustion chamber before top dead centre, but also reduces the charge motion turbulence intensity. So there's a trade-off between the higher knock resistance due to lower combustion temperature and the lower knock resistance due to the lower turbulence intensity. Another way of looking at this is that the work done by the piston during compression is lower because the first few degrees from bottom dead centre on the compression stroke are spent returning the cylinder to manifold pressure, balancing the work done, less the losses of course, to reduce the pressure from the manifold to that at bottom dead centre. The solution is to maximise the upsides of the Miller cycle and mitigate the downsides by adding additional turbulence intensity in the combustion chamber. So two examples of this technology, one of which we've discussed already, is the pre-chamber spark plug, and the other is the Omega bowl piston, which we'll discuss next. However, before we leave the Miller cycle, high valve accelerations are critical to maximise performance. So the mechanical limits of valve gear and valve drive are crucial limitations. Other important aspects to balance are the boost pressure, the field properties, the compression ratio, the residual gas scavenging, the intake port geometry and length, and the effect of any crank offsetting. But let's have a look at the valve timing on this Miller cycle before we leave it, and look at the embodiment of it. So if you look at the cam curves here, as an approximation, while the intake valve is slightly open, the pressure in the cylinder during induction is about the same as manifold pressure. By closing the intake valve early, the combustion chamber becomes effectively a sealed volume before the piston reaches bottom dead centre. So the pressure then falls below manifold pressure as the piston moves to bottom dead centre. As the piston starts to come back up, it reaches a position where the chamber became effectively a sealed volume on the way down, and the pressure would now be back to manifold pressure, but the compression stroke is already underway. So there's a shorter compression left to act on the manifold pressure. So the compression ratio is less than the geometric compression ratio. Now one thing you will see here is that the Miller valve lift is much lower than the conventional valve lift. And this comes from the fact that all the lifts on a racing engine are limited by mechanical considerations in the valve gear stress. If a valve could be accelerated faster to open more quickly, it would be. A racing engine valve lift curve is at the absolute limits of mechanical integrity. So if you've got to open and close that valve over fewer degrees, for the given acceleration limits that you have, you can't open it as far. Now, if we still had an air-limited engine, this would be catastrophic for airflow at a given capacity or RPM. But for the fuel-limited engine, you can increase the boost to compensate. Of course, this does take some additional turbo compressor power, but the net gain in efficiency and power at a given fuel flow is certainly worthwhile. A further enhancement that's relevant to this type of engine is the shape of the piston crown, and I mentioned the Omega bowl a minute ago. So short-stroke engines don't really allow high tumble concepts. an Omega bowl piston is a combination with squish achieving the necessary turbulence intensity for a fast and thermodynamically efficient combustion. We have very low valve angles, around 5 to 7 degrees, and this improves the squish geometry. But the concentration of the total turbulence intensity is really there because of the Omega bowl, and this leads to a faster combustion at the beginning, but results in a slower flame speed and less turbulence intensity above and outside the Omega bowl at the end of combustion. The other part, of course, is the fuel. We can't have good combustion if we haven't got good fuel. And with such a complex combustion system, the interaction between the mechanical design, the ignition control and the fuel is much more critical than in a more conventional engine. So let's look a little at the fuel itself and some of the aspects of combustion. The modelling that we've carried out in conjunction with Cranfield University has helped us to understand the critical aspects of the combustion process. While we don't pretend to understand it to the level required of the engine designers, we feel it's necessary to go a bit beyond the basics if we're to advise on future regulations. And some of the points we've learnt are that high lambda values we achieve depend as much on the compressor size when boosting to values as high as 5.5 bar as they do on the thermodynamic desire to run lean. At full load above 9,000 RPM, we have about 50% mass fraction burnt around 8 degrees after top dead centre. And the ignition point really depends an awful lot on the pre-chamber geometry. At around 1 or 2% mass fraction burnt of flame, or in fact the radical jets of the pre-chamber, hit the main combustion chamber. And this small amount of combustion does not contribute much to the mechanical work, as the heat dissipates mainly into the wall of the pre-chamber. Additionally, for compression of the remaining gas behind the electrode in the pre-chamber, a late ignition point is always beneficial because of the high pressure inside the chamber. The combustion slows as the piston moves down, depending on the detail of the Omega bowl design. So this leads to a relatively quick combustion from around 2% to 80% mass fraction burnt, and slow combustion from 80% mass fraction burnt onwards. Speeding the combustion up here is doubly advantageous because slow combustion, of course, is going to encourage knocking. So fuel is a key parameter in maximising our performance when we're knock limited. And there will always be a trade-off between the energy content and the knock performance. So while we're always looking for a very high energy content in our fuel, we've been told that if you reduce the RON by around 3, it will result in around 6% less peak performance. And of course 3 is, give or take, 3%. And you're losing 6% of performance from that. Whereas if you reduce the LHV by 3%, you're going to lose a similar amount of performance. So the fuel for the current engines is really the result of exploring boundaries within really some quite unnatural limits imposed by the regulations. Not just regulations imposed on the fuel itself and the flow rate limits, but also relating to the constraints on the engine type and the geometry. So the fine-tuning of the fuel will be very engine specific. Now, our intention in Formula One is to move away from these highly specialised fuels to a fuel that is both sustainable and slightly closer to the requirements of less exotic engines, in other words, more of a drop-in fuel. We have a comprehensive definition of sustainable fuels, and we have an outline of the specification of our future non-fossil fuels. But if we look at the current fuels, some of the typical properties, obviously because we are fuel limited, we want the highest lower heating value that we can get. So LHV typically 43.5, 44, so much higher than you'll find in a regular gasoline. RON again, because it helps to mitigate against knocking, 103.8, 104.2 in those sort of regions. So again, above that of conventional fuels. And we have a MON of about 86, 87. But we now have fuel simulations that are good enough to allow us to do a lot of virtual development. So we use a virtual reactor to burn individual fuel components, looking at auto ignition time and looking at laminar flame speed. So it allows us to do an awful lot of development, and we're working closely with Aramco, who are one of our main sponsors on this. The LHV of the current fuels is vital, as I've said, and that's a result of the mass flow limits. And this necessitates the use of high levels of isoparaffins, olefins and naphthalene. The important detail is that the aromatics are only used at very low levels or even removed altogether because the LHV of the aromatics is too low. And this really is the main reason why Formula One fuels depart in composition from mainstream petrol. So our research now is focused on sustainable fuels, which will be regulated not by mass flow but by energy flow, with the emphasis on leaving freedom to develop fuels and methodologies without an arms race and to produce fuels that are more road relevant. So our thinking there is that if we define, instead of the flow rate into the engine and assuming that the LHV is around 44, we're actually going to measure the LHV of the fuels, and we're going to say, right, you can inject so many megajoules per second of fuel into the engine. And this, we hope, will encourage the fuel manufacturers to look at various different ways of producing sustainable fuels. But today, these are the typical compositions of the fuels. So where could this all go? Where could it take us? I think one of our desires is to reduce the fuel flow even further, and I'm talking some years out now. We do this with an increase in electrical power and, most importantly, with active aerodynamics on the car to reduce the drag, because one of the reasons we need so much power is that we are pushing a bit of a brick around, with a CD of well over 1 at the moment. Now, if we reduce the fuel flow, it may promote even leaner running, and our simulations show that with a passive pre-chamber and the fuel flow reduced to around 70% of current values, it could be possible to run as lean as Lambda 2 with acceptable knock characteristics. I think it would be unlikely, however, that we could achieve 70% of current IMechE values. So this loss of efficiency would be accompanied by probably higher unburnt hydrocarbons, but at Lambda 2 we would have significantly lower NOx. If we were to allow an active pre-chamber, in other words, if we changed our regulations to allow 2 injectors per cylinder to be used, it really does become a lot easier. At 70% fuel flow and at Lambda 2, we can certainly achieve 70% IMechE with virtually no unburnt fuel and equally low NOx values due to the cooler combustion. We could go further, and a larger engine with a longer stroke-to-bore ratio running at lower speed could be even more efficient. But ultimately, we must remember what we're trying to do, and we're here to produce the greatest racing spectacle on the planet. And that means noise, and it means power, but it also means that we have to do it in a sustainable fashion. So I hope during the course of my talk I've given you some insight into how these engines work. I've not designed an engine myself, and as I said, the engine people are sometimes quite reluctant to tell us all the details of how they work, but through our research we've figured out a lot of what goes on with them. So with that, I'll try and field any questions, but I would remind you I'm a chassis guy, so be easy on me.
Thank you very much, Pat. Terrific. Forgive me for touching this so I can keep an eye on the online questions as well. So I have to sit here so I can read it all. But yeah, go ahead. Who would like to go first? I'm sure there's going to be loads of questions on this. Oh, straight away, there we go. If you could just shout out who you are and your affiliation, it will be a huge help for everybody who's online, if that's okay. Thank you.
Paul Smith. I'm retired. Sorry, Paul Smith. I'm a retired engineer. 2 questions really. When you said the compression ratio is 18:1, was that the geometric compression ratio?
That's geometric compression ratio, right. Yes.
Okay.
And
And
we
second-
have the world's most complicated way of defining the geometric compression ratio. It's about a page of our regulations.
And the second question is, HCCI is usually only used at very low loads, so I wonder where you use that, and isn't it contradiction in terms when you say spark assisted, HCCI?
Yeah, exactly. We have a spark plug there.
It's not compression ignition then?
Yeah, we are very close to compression ignition. So that's what the point I was making there was that, it's difficult to describe this in a classical way of saying it's this type of combustion or it's that type of combustion. It's a little bit of everything. The control systems that run these engines are pretty sophisticated. So there are NOx sensors on each cylinder. And basically you run them right up to the NOx levels that you are comfortable with. And then you start to back off the spark from there.
Right.
Equally, we have some quite sophisticated damage models now. So in the old days where you said, well, an engine had a life of 500 miles and then you changed it, and if you over-revved it, you pulled it out. The damage models on these engines are incredibly sophisticated, and they'll be looking at every aspect that's going on with multiple sensors through the engine. And the life of the engine and the duty cycle that you run it at are very dependent on these lifing models. So obviously there are different modes. I talked about some of the hybrid modes, but there are also different modes in the internal combustion engine. Now the rules at the moment mean that you have to run one mode all the way through qualifying in the race, but I think a lot of you know that there used to be different modes with a lot of advance, running the fuel flow right up on the 100 kilogram limit for qualifying, and then bringing everything back a little bit for the race. Now, they don't do that anymore. They have to find the compromise, but the damage models help them to achieve that.
Right. Thank you.
Excellent. Thanks. Next. Yeah, we got one there. Andrew? I think that's Andrew over my glasses. Yeah, it is.
Yes, Andrew. Thank you. Excellent presentation. Thank you, Pat. Andrew Fraser from Zemo Partnership and IMechE Automobile Division. In pushing the boundaries of the combustion system so hard, are the control systems using in-cylinder pressure sensing to manage? So there are individual pressure sensors on each cylinder. Yeah, I thought there would have to be.
Yes.
That's part of the advanced control system you talked about.
Yeah, it's a very important part of it. It's a difficult part. It's a very expensive sensor. It's not the most reliable sensor, as you can imagine, because it has a pretty hard life. We're actually talking at the moment about our 2026 engine, and one of the things we may do is eliminate those sensors because of cost. Now, one of the things we want to do in 2026 is bring the cost down. Now, this is Formula One, so when you say you can't have a NOx sensor, the first thing you do is you think, well, how can I measure NOx without a NOx sensor? So you have to be very careful not to eliminate the obvious way of doing things, thinking you're saving money, and then actually have something that's much more complex that costs a lot more money. But we're happy with basically accelerometers and things on cylinder heads because they're quite cheap, but the in-cylinder pressure sensors are a very integral part of the control at the moment.
Yeah, thank you. Yeah, in my former life, we looked at that hard for production engines, but the cost for a volume production engine made them prohibitive, so I was interested to know if you'd deploy them. Thank you.
Yeah, we have the luxury of our engines cost, well over $1 million.
Okay, thanks. I'm just going to go to one online question and I'll come back to you in a minute. I was just talking about the road relevance. Pat has come up on a couple of things about MGUH and what have you, but it was a very good question about what could you do with variable valve time? Is that something that's not allowed at the moment? Could that give you some more benefit? And I'm thinking particularly around millicycle, being able to maximise the boosting, for example. So,
yeah, I think it could, Steve, but variable valve timing is very good when you've got an engine that has to operate through a lot of different regimes. Yeah. We really do design our engines to run full load, and they're running wide open throttle nearly all the time. or closed throttle, and very little in between. You know, a little bit of tiptoeing out of the corner, but that doesn't last long, believe me. So we really focus on the efficiency at full power. And if you think of a conventional engine and you look at the brake-specific fuel consumption curves, you know, the classic fishhooks, they're nothing like that on the Formula One engine. Our best BSFC is at full power. And yeah, that's because that's where we operate.
Excellent. Yeah, sure. Go ahead. You remember your name and affiliation.
Thank you very much. Oliver Joris, Ford Motor Company and Automobile Division. Thank you again for your talk. Very interesting. One of the things I feel is perhaps a great opportunity in terms of transferable technology is some of the things you talked about in terms of fuels. I know biofuels have got a bad rep for some good reasons, but the synthetic fuels have a real opportunity to match some of the things we're doing and perhaps improve some of the fuels we're accustomed to. What are your thoughts on how the work that you're doing will influence perhaps mainstream usage of fuels and how that will help with some of the, you know, lowering our carbon intensity?
Yeah, that's a really good question. Did you say you're from Ford? Yeah. So Carsten Weber, I think, is very keen on this, if you can get him away from his methanol. But yeah, I mean, this is probably our biggest push at the moment. There are racing series that are going on to biofuels, to e-fuels. It's quite difficult for us. It's very easy. In fact, we will introduce sustainable fuels into Formula 2 and Formula 3 before we do into Formula 1. And the reason for that is that Formula 2 and Formula 3 use a single type of engine and they use a single type of fuel. So we've got to do the job once. And to be honest, it doesn't have to be perfect. With Formula 1, we have multiple fuel companies involved. We have different types of engine, and it does have to be perfect. We can't formulate a fuel which would advantage one engine against another. So it's a big problem. We also use a reasonable amount of fuel. We use around 1 million litres a year. Now, that's not much in real terms, but it falls between two stools. It's a little bit too much to make in the laboratory. It's not enough to make in a proper plant. Now, there are decent pilot plants being built, and in 2023 there'll be at least 2 that we're involved with will be on stream. And we are really pushing this. This is really important to us. As Steve knows, we talk about it all the time. We have I just happen to have it in front of me. We have a very comprehensive definition of our advanced sustainable fuels. So we're not doing any greenwashing, but it's got to be correct. And we really are great believers in this. We really believe that an advanced sustainable fuel, providing it's a drop-in fuel, it really can contribute to parallel paths to electrification. And it's one of the reasons why I said that, you know, as we move forward on our fuels, we will bring RON down. We will make them much more road relevant. By going to an energy content, we really feel that what we can do is we can push the technologies. You know, where do you get the carbon from? How are you going to capture that carbon? We want to promote everything from direct air capture through all these sort of biological processes. But what we want to do is produce a good fuel with a reasonably high lower heating value that can drop into the billions of vehicles that are on the road at the moment, using the infrastructure that we've got. And even if urban vehicles do go electrified, all these other heavy vehicles, trucks and things, you know, that will need a really high energy density power unit and fuel source, or energy source, it's great for it. I was on a call with Steve today, and I was quite amused that they're talking about even combine harvesters. You can't put a heavy battery in a combine harvester because it sinks into the ground. And you know, there are all sorts of reasons why there will be internal combustion engines around for a while yet. And this is something that can actually make them something we can be proud of. And in Formula One, we have a little strap line that we continually tell ourselves that Formula One fans must be proud to be Formula One fans. They must never be ashamed of being a Formula One fan. So unless we can move to sustainable fuels, people will start to be criticising us, and quite rightly so. So it's a really, really important part of our future strategy.
Okie dokes. Another one of the online questions I've made a note of, which was, we've talked about the engine next, if you see what I mean, a sustainable fuel. Where do you think the engine might go? What sort of things might you be considering? We won't tell anybody.
Well, Steve, I've got a lot of grey hair, so maybe I don't have to worry about it too much. I think I pride myself on being able to look a little bit into the future and see where things are going, but I don't think anyone can do that at the moment. What we've got legislation that's driving mobility in a certain direction, because that legislation is legislating process rather than outcome, and that's not a great thing to do. I think, if the world had said, we don't care how you do it, but just reduce CO2 from small vehicles, yeah, of course there'd have been electrification, but there would have been other things as well. But legislation has driven this sort of great drive to electrification. And I guess what's on our minds is, will we meet those targets? Is it true that in 2030, you really won't be able to buy internal combustion engine vehicles? I'm not sure it is. So things are changing so rapidly, it's really hard to try and figure out where the next one is. So we're working on 2026 at the moment. What we've done with that is, at the behest of the manufacturers, our main thing has been cost down, because these engines have got very expensive. So we've done a lot of work on trying to bring the cost of the engine down. We have increased, or we will increase, the electrical power, so much more hybridisation, and we'll be approaching 50-50 internal combustion engine and electric power. Not quite, but approaching it. And that will give us some time. But I think beyond that, it's very hard to say where we'll be.
I was expecting you to say something around two-strokes and split cycles.
Well, Steve, I'm a great fan of two-strokes. I do think that two-strokes suffer from a bad reputation, but a modern two-stroke with this sort of technology, I think is really excellent. Split cycles are great, but power density is the killer there. And you're carrying around extra cylinders. Yes, you can get high efficiency, but split cycle is for other uses, I think.
Playing. Right, any more questions from
And-
you?
and
There
no
we go,
one-
crikey, that's started them all off now.
And no one mentioned hydrogen.
It's my last question. I've got one about hydrogen. Yes, I'll go over the top of Andrew first.
I'm a graduate from University of Bath, just finished. Just had a couple of questions about the thermal efficiency. So the values you've stated, like 50%, 30%, is that just on the dyno, a single operating point?
It is at maximum power, yes.
Right.
So the strict answer is yes. But we've got pretty good efficiency all the time. We're on maximum power.
Right, so I was just wondering, what would you typically see in a race, for example? I know it would depend on track and conditions, but just wondering how much it changes.
As an average?
Yeah.
I honestly don't know the answer to that. The engine guys would know the answer, but they're not very keen on sharing.
Yeah, that's
those sort of
understandable.
things with us.
And the other question I had is just about the 50% efficiency of the current engines. How much of that is down to the improvements in the IC itself, and how much of it is due to the hybrid system, do you think?
Well, we're talking about the thermal efficiency. We're talking about the ICE.
So that's
efficiency.
without the MGUK?
That's without the MGUK.
Right, okay.
Yeah,
But with
Thank
the
you.
MGOH.
but with the H, yes.
Yeah, okay, thank you.